On paper, this jet shouldn't even exist. At Mach 2.5, the air outside is hotter than molten steel. The engines are pushing more fuel per second than a small city uses in an hour. And yet, engineers somehow built a machine that, literally turned into fire mid-flight. What went wrong, and why this failure teaches us more about engineering than any success ever could, starts with one stubborn problem: heat. During the Cold War, military planners demanded an aircraft that could strike targets faster than radar could react. Speed wasn't just a luxury, it was survival. The physics were unforgiving. To go Mach 2.5, you're not just fighting air resistance, you're fighting the air itself. Visual, slow pan across a map of Cold War-era missile targets and airbases. Visual, overlay arrows showing shock waves forming on a fast-moving jet. At these speeds, the kinetic energy of the plane turns the skin of the aircraft into a furnace. Aluminum, the backbone of conventional jets, starts to lose strength at just 400 degrees Celsius. That's barely hot enough to melt chocolate. Now imagine trying to stay solid at 800 degrees Celsius or more. Air friction isn't gentle. The faster you go, the more heat the air drags onto your fuselage. This isn't just uncomfortable, it's catastrophic. Once the skin temperature approaches its melting point, structural integrity collapses. The wings bend. The engines fail. The jet ignites. And it's not just metals. Jet fuel itself burns hotter than the skin can tolerate. The chemical energy that propels the plane is literally capable of turning it into a fireball if not properly controlled. Enter the hero: high-temperature titanium alloys and ceramic composites. These materials can endure temperatures above 1000 degrees Celsius. But strength isn't enough. Engineers also had to design active cooling channels inside the fuselage and leading edges. Visual, exploded 3D model showing internal cooling channels in wings and fuselage. Visual, close-up of turbine blades coated with thermal barrier ceramics. By using a combination of hollow structures, heat-resistant coatings, and clever airflow management, the engineers essentially built a jet that could survive an oven at nearly twice the temperature of a blast furnace. But every solution has a price. These materials are incredibly expensive. The jets are heavier, which paradoxically reduces efficiency. Maintenance costs skyrocket. And even with advanced materials, pushing past Mach 2.5 still risks catastrophic failure, as history painfully showed. In short, engineering this jet was an exercise in compromise: speed versus durability, weight versus heat tolerance, cost versus performance. So, is this technology ready for everyday use? Not yet. The physics don't lie. Even the most advanced alloys and cooling systems can't make fireproof humans, or cheap, sustainable jets at this speed. But as a demonstration of human ingenuity, it's a marvel. It proves we can challenge nature's limits, even if only for a few minutes of supersonic flight. Sometimes, the most powerful lesson in engineering comes not from what survives, but from what burns. High-speed flight, pushing materials to their absolute limit.